Good morning, everyone. Thanks for attending this morning session, and I hope you had a great time during the conference with dinner last night. And today we have two morning sessions that covers the contribution from India to SKA and also the progenitor models and FRB emissions thing. So in the first morning session, we have three talks from Prabu, Sahana, and Clarinda mainly about the SKA and the progenitor models. So I'm happy to introduce our Prabu for the SKA transient search pipeline and developments. So let's welcome Prabu.
Good morning, everyone, and nice to be here for this FTSky and thank the organizers for arranging this program. And first of all, I have to say my sincere thanks to all my colleagues, friends, and students who are interacted. First of all, they are the reason for the amount of learning that understanding that one could have on this work. So my talk would be mostly from the learnings. As I have perceived, and it's my view of the work, and I take responsibility for anything missed out or overemphasized. So there's a history part I will touch upon, and then I'll go into just give a feel for how the search pipeline for the SKA, for the fast transients, and also highlight in such big projects two of the bottom two items. One is the student contributions and also aspects related to managing bigger projects, such as the several ones that are happening now, including the SKA. So long back in 2012, Ron Akers put in this plot to show how the telescopes have evolved and their sensitivities have grown over time. And as you would see, their sensitivities have grown since the first telescope, which Grotreber has made, to what is now we are talking about the SKA and Geomarti, and the VLA just next to the SKA here. So these sensitivities have doubled every approximately 3 years, a kind of an exponential growth. And these sensitive telescopes have also yielded in the discovery. The more the sensitive the telescope, the weaker the signal it can detect. It not just means they are just weak, it could also be from a far away distances. So we are probing the dimensions more better with these sensitive telescopes. So over the time, variety of events, particularly with the pulsar signs, have happened. And it's remarkable that we are now expecting manifold further discoveries from the known transients so far. I have not put the FRB plot here. Those numbers are 1,000 close. And now on the chart here, it shows the better the technology, the better the discovery rates among the discovered pulsar until this timeline. The Parkes 13 beam produced more discoveries, Arecibo 7 beams, Green Bank, the bigger telescope, and things of that kind you can see with discovery happening with bigger and sensitive telescopes. Going still before this, why do we have to again search for many of these pulsars? Thanks to these slides that I could collect this morning, very long back in the 90s, 80s and 90s, just at about 20 years since the pulsars have been discovered, this pulsar life cycle plot put forward by Srinivasan was just a speculation at that time. With statistics improved and further work by his own students and people across the world, clearly shows this is what indeed is true, and we are now able to identify aggressive pulsars and graceful pulsars and very artful, very green pulsar which would live forever. I mean, again, quoted by Srinivasan, these millisecond pulsars are harmonious with the universe and they would live forever. Possibly stated it in the same lecture hall some years back. So it is possible to go from theory to what we observe and they match, and that kind of a thing has happened. Now, going back again to the SKA, the concept of SKA had come up pre-1990. I have put in, there are Dutch people involved, Canadian people involved, thinking about big telescope. In the context of the event happening here in India, I put in Govind's, highlight Govind's thought of building big telescopes, which eventually led to the GMRT, and the name of SK itself came about much later in a 1998 time frame. And one interesting thing happened was countries agreed to cooperate in developing technology for the SKA way back in 1997, which is quite significant. Coming back again, people knew it's not going to be that easy, and wide radio spectrum, one would need not the same kind of antennas, it's not same kind of dish antennas or the dipole antennas. It has to be different for the different frequencies. So that was identified much in advance. And also it was not clear where do you draw the line between the dish antennas and aperture antennas. That was a question that was still, even now, people have it. And it's way back in 2012. Okay. And it was also realized electronics is developing enormously, and we could make use of them. But on that day, on that time scale, 2008 and 2012 scales, people knew it was not existing. That electronics that was required was not existing. But they realized with time, when the technology, when the developmental ideas evolve, one can make use of the available technology. And it was also thought of using commercial off-the-shelf components as much as possible. And countries would build different prototypes, and key technologies, exact technology will be decided later. And it was also thought about avoiding duplicate efforts and achieve reasonable cost. Very well framed set of points. And it has actually driven almost in the same way until now when the SKA is being built. So as a, I think I've not skipped a slide, yeah. So I'm just highlighting a variety of efforts that went in finalizing the antenna effort over years and years of effort by different groups who have worked to specialize with specialized abilities to come out with an antenna array configuration, particularly the aperture array configuration, and including the phased array feeds and Vivaldi arrays. And those of you who would visit GMRT would see one, and if you happen to be from that part of the world, you will see these arrays in action in some other part of the observatories too. So variety of choices considered, and multi-pixel feeds and variety of things have been thought about. You will see still when the square kilometer array is being now realized, some of these points still remain unanswered, and it was decided to build a two-phase telescope, mainly because some of the technologies are still not there. And international collaboration is going on, aiming to provide continuous coverage up to 25 gigahertz all the way from 50 megahertz. I'll move on. Currently, as of now, as we stand, the radio quiet sites in two best part of the world, two of the best radio quiet spots have been identified. One in South Africa, one in Western Australia, and with the headquarters in UK. And it's actually 3-part and 1 telescope, and 197 dishes in one of the South African array, and about 0.1 million telescopes in the Western Australian desert. Move on. The signal flow for both the telescopes approximately is similar, except some parameters change. And the South African telescope on the left and the Western Australian telescope in the middle, they both will have a field programmable gate array and RF electronics in the field to handle the high-speed data, digitize the data, and transmit them through optical fibers to high-performance computing domain where large amount of FPGAs as well as GPUs have been heavily used for the computing purpose. For the purpose of convenience, there are processing subsequent to forming the beams divided into two. One is an imaging group, which works the visibility data and work on it, and the non-imaging, which is covering the transients, fast transients, and VLBI, etc. And then the data goes through the global network. So SKA has been built with 8 science goals, major ones, cover at least in 3 of them pulsars, transients, and so on. Okay. And now it also now opens up a window into the gravitational wave astronomy, where the pulsar studies have make connection and impacts the PTA science. Traditionally, as you know, the observations have happened in a manner that was very, very simple scales, and pulsar observations were recorded in a chart recorder such as this. And I'm just going to pass it on. This is from the OT telescope. And that has moved into now we can do a real-time observations. You have to collect the data earlier and then process it offline. What you see there is a 0950 pulsar, single pulses directly recorded in the chart recorders. So now the complexity is what was done in offline processing, traditional processing, antenna signals, signal process conditioning, digitization, and it divides into correlator and the beamform data for pulsar kind of science. And they were recorded in offline process. Now with the maturity of electronics, algorithms, and confidence with which we can deal with the data, we can now do them in real time. However, it is a heavy computing challenge. So now there are a variety of things that makes this science searching for more pulsars is being still very attractive. And one would like to look at, I've listed all of them and would go into few. It is important to know how the spin period evolves, and their rate distributions in a plot like that could give some clue about their birthplace. And also interesting to know what could be the slowest and the fastest spin period, just to get to know how do they look around those imaginary death lines that we have and the recycling phenomena. And also, what is the connection between the FRB kind of signals that we get, possibly the magnetas and other kind of radio pulsars themselves. So one would also like to know about the proper motions, and that will also tell us where they possibly originated from. It needs high astrometry, high accurate, high resolution astrometry, and obviously these things cannot be done just like that with the simple telescopes. And one would probably need a large baselines and sensitive enough telescopes and broad frequency coverage. So again, one would be interested in knowing even the masses of the neutron stars. So that's going to give lots of information about their formation, evolution, and also will have implication in the pulsar timing. Now, these things are expected to increase when the big telescope, big surveys start and the transient search pipelines start working. So it is expected these telescopes are going to give several milli-arcsecond accuracy to their position measurements. And also the distance measurement through the DMs can also be very precise, best possible precision that we can get. Now, going further, so building a pipeline, search pipeline, involve dealing with variety of things, and it is a high compute intensive task, as you would also hear a little more later. I would be skipping and dealing with the data, for example, 60 petabytes per day, and these numbers are huge even today. And dealing with a large range of DM is a huge task indeed. And while searching, and the same thing applies for all the transient blocks involved in the search pipeline, pulsars, FRB kind of single pulse search pipeline, and so on. And also the algorithm behaves differently when the pulse width varies. And we have a variety of these bits that we have seen, and that helps to build a better algorithm definitely. Okay. And on top of it, some of the pulsars of interest happen to be in a binary orbit around another star. And the Doppler orbital motion smears our search sensitivity. One needs to build enough deacceleration in the pipeline, and that has to be done in real time for a variety of accelerations. So hence, it is indeed a tough job. And the last but not the least, but it seems to go into a topmost part after attending this FTSky conference, for me at least, is dealing with RFI. So ideally, dealing with RFI, now there will have to be RFI pipeline that may have to emerge in the future telescope. Terrestrial technosignatures, extraterrestrial technosignatures, biosignatures, and also somebody else's science. Okay, so what you discard could be someone else's science or someone else's matter of interest. So I suspect it will become a pipeline by itself. So variety of machine learning techniques have been tried and being used. And as you go, the pipeline looks in a simplified form look like this. Colleagues here, Jayanta, Bhaswati, have worked during the critical design of this particular pipeline in shaping, particularly Jayanta's contribution in several areas, including the single pulse pipeline, was very significant. And so the pipeline starts with 5 more minutes. Okay. So pipeline starts with the typical any RFI removal, the dispersion, and the single pulse detection and optimization, and then it goes to science data processor. And for the pulsar, periodic signals, and there are, again, the Fourier transform, removing the known RFIs in the spectrum, de-reddening the spectrum, acceleration search, candidate shifting, candidate folding, and then to the science paper. And a hardware accelerators have been used, being considered. Let me put it like that, because telescope is to get them fully. And the next talk, you'll hear more on the shifting from Sana. So at this point, as we build big telescope, it's important to pay, or even big projects, important to pay attention to involve the students, and we had an opportunity to get them involved too. And this is one of the first of the kind for the Intel or the Altera FPGA DevOps, the way software is developed for by this professional softwares. FPGA firmware could also be developed using GitLab and Git repository and following GitLab procedures. So one of the students developed the very first prototype, and it's now actually being followed in the SKA Pulsar group. And it's an undergraduate student in the 3rd year. So the potential is enormous. And going further, another student who passed out of the graduation developed a machine learning for detecting the, so 2023, 22, the work was done, detecting the accelerator signals in the filter output plane, we call, using an hourglass model. It is not this bow tie we refer to as an hourglass model. And the acceleration due to the Doppler motion in the filter template matched output, this is how the signal appears, and that could be very easily captured by a machine learning technique. What was used was a mask RCNN, and there's a reference here. Okay, now going further, I'm close to the last few slides, and it is concern. It's a global concern. SKA did emphasize this in our midst when we were working on it. Our performance in our situations, in some country situations, power is not too much as a botheration. And some places in the deserts and so on, as you consume more power, you also pay more tariff, more cost for that. And also there's a limitation, ceiling. And on top of it, this power comes from fossils, burning them, or from sometimes renewable energy. So the more computing also means more gigaflops you can deliver, but it also means it consumes more wattage. This is a real simulation based on the chips performance, whatever they have given. That what, as you see, more gigaflops, more watts. So it's only for one chip, hundreds of chips in a data center, which is running for this data processing. So we are looking at these also. We optimized our computing by using FPGAs, which at that point delivered very good power performance. It's a concern. The work on the same line is under review. And now going further, quickly, another lesson that I wanted to pass it on is typically we used to build designs. We get the team knows what exactly you want to build, very high confidence on the requirements. Once the requirements are defined, the team goes into the design, they go into some place, some closed room, and then go and come back, say, I have the design ready. That's how systems have been built. That's such a kind of approach we call is a waterfall approach. It works okay. It worked okay in our labs, many places. But when it comes to bigger projects, that method seems to have problems. Somebody comes out with the wrong result, and it will not match with another person's work. So now, the method that people follow is called Agile, and this is practiced very well in the SKA, and some of the successful labs, successful industries do follow this without actually naming them as Agile. So where there is an iterative improvement and continuous delivery of some results, continuous checking, and also end-to-end, and individuals' interactions matter more than process and tools. Working design is more matter than a comprehensive documentation alone. A collaborative work with the end user, who is a user, science user, is more important, and it's a requirement that should not be fixed at the beginning itself. And responding to changes, some things may work, may not work. So I am going to skip this, basically telling the 12 different principles. If you have looked at it, I'll skip quickly to the next slide to say thank you.
Thanks, Prabu. It was a nice comprehensive details about the SKA pulsar pipeline. So my question is that, you talked about FPGA. So as I understand that, is it like talking about both the transient and pulsar search pipeline is going to sit on FPGA, or there are some GPU components also on it?
No, actually currently, let me go quickly back to that slide. Probably you also know. All of these boxes with a small circle have been explored in the FPGA, but for implementation that may not be carried forward because there are a variety of very well matured algorithms, and when the requirements continuously change, it's probably the GPU scores better. So, but most likely, a lot of work has happened on the acceleration search on FPGA. It's likely to be one candidate, FPGA candidate for the search.
Great. Thank you. Any other question? I have a very simple question about the, maybe you have covered, but I'm wondering whether you have some timeline of the work to be done in India for SKA?
Yeah, the timeline have been slightly slipping as it has been happening in many different projects as well, because about 13 plus countries are involved, their funding and industry, and COVID came in the middle. We definitely slipped the timeline. As you would have seen in my first plot itself, the SKA had pushed an right hand side. But now 2030, you have an operational telescope. 2027, we'll have a test data.
Yeah. You're also working on the beamforming development, which will cover by Sahana. So